Hi everyone, we will be covering and teaching question 7 for our application of derivatives. However, before we dive into the math, I want you to think about why we even have to do this. Optimization is essentially all about finding the best possible version of something within a set of strict rules. In the real world, this is how engineers design fuel-efficient wings or how companies minimize packaging waste while keeping their products safe. Today we're looking at a classic geometric constraint. We have a specific right angle triangle with side lengths 5, 12, and 13, and our goal is to fit a rectangle inside of it. Now, you could draw a tall, skinny rectangle or a short, wide one, but only one specific set of dimensions will yield to the absolute largest area. That sweet spot is what we're hunting for using derivatives. So here you can see our catalog where everything is going to be. But once again, before we move into our next slide, it's important to recognize where we're putting our rectangle because the wrong visualization can completely mess you up when it comes to these sort of problems. So let me read the full question for you now. Given a triangle of sides 5, 12, and 13 centimeters, a rectangle is inscribed in the triangle such that two sides of the rectangle lie along the two shorter sides of the triangle. The remaining vertex lies on the hypotenuse. Find the area of the largest triangle. All right, so as we was aforementioned, we have our sides of 5, 12, and 13 centimeters, and our rectangle has or must live by three very specific laws. First, two sides must lie directly along the two shorter legs of our triangle on the 5 centimeter and 12 centimeter sides. Second, the corner opposite the origin must sit exactly on the hypotenuse. This is our limiting factor. If that corner wasn't forced to touch the diagonal line, we could make the rectangle as big as we wanted, but the hypotenuse acts as a ceiling that gets lower as we move to the right. Our goal is to express this ceiling mathematically so we can find where the area function peaks. On your worksheet under section 1, I want you to underline those three constraints because they are the only reason this problem requires calculus instead of just basic area formulas. Now, how do we turn a physical shape into something a computer or a derivative can understand? We have to translate geometry into analytic geometry. Imagine overlaying a grid on our triangle. By placing the 90 degrees vertex directly at the origin 0, 0, we turn the triangle legs into our x and y axis. This is a strategic move. It means the base of our triangle now lies along the x-axis from 0 to 12, and the height climbs the y-axis from 0 to 5. More importantly, it turns that diagonal hypotenuse into a linear function instead of a slanted line. It becomes a path defined by a slope and a y-intercept. This transition is the engine of representation, and without this coordinate shift, we'd be stuck measuring with rulers instead of calculating with power rules. So we have our world established, we have a triangle on a grid, and we have the rectangle whose top right corner is a moving point, xy, that must follow the hypotenuse. But here's the problem. The area of the triangle is area equals a equals x times y, or area equals width times height. In this course, we don't like having two different variables in one function. It makes the derivative messy. To solve this, we need to find a way to replace that y with something that only uses x. On your worksheet, you can look at the linear equation section, and this is where we bridge the gap from shapes to equations.
Alright, now that we have our triangle sitting on the coordinate plane, we need to find a mathematical way to describe the diagonal line, the hypotenuse. In our coordinate system, the triangle corners are at 0, 0, 12, 0, and 0, 5. To get the equation of the hypotenuse, we first need to find the slope, which is just rise over run. Since the line goes down 5 units as it moves 12 units to the right, our slope m is negative 5 over 12. Because the line crosses the vertical axis at 5, our y-intercept b is 5. Putting that together, we have our constant equation, y equals negative 5 over 12x plus 5. This equation is the heart of our problem because it tells us exactly how tall our rectangle can be for any given width x. If you look at section 2 of your worksheet, go ahead and calculate that slope yourself to make sure you see where that negative 5 over 12 comes from. But now let's talk about what we're trying to maximize, the area. We all know that the area equals width times height, which are on our graph is just area, which is x times y. But here's the challenge. If we try to take the derivative of x times y now, we'd be stuck with two variables. This is where we use the substitution method. We take our equation from y from the previous slide and plug it directly into our area formula, which gives us x times negative 5 over 12x plus 5. When we distribute that x, we get a single variable quadratic function. Area x is equal to negative 5 over 12x squared plus 5x. This is a huge win. We have officially turned our geometry problem into a standard calculus problem that we can now solve using derivatives. Now, before we actually do any math, let's look at the logic on slide 7. We have our area function, area x is equal to negative 5 over 12x squared plus 5x. This isn't just a random equation. It's like the story of growth and decay. If we were to graph the area function, you'd see that it starts at 0, where the rectangle is all height and no width, climb up to a peak, and then fall back to 0, where the rectangle is all width and no height. We know that the peak or the maximum occurs exactly when the slope of that curve is 0. In other words, the point where the area stops growing and starts shrinking is our winner. To find that exact point, we need to take the derivative of our area function and solve for when it equals 0. This is the moment where we move from modeling the problem to actually solving it. If the derivative tells us the slope of the area function, what does it mean if our derivative is a positive number at a certain x value? It means the area is still growing. If the slope is positive, we haven't reached the peak yet. We only stop once that derivative hits exactly 0. Now that we know we need to find where the derivative is 0, which specific rule are we going to use on this quadratic equation? The power rule. Now it's time for the actual differentiation.
All right, so let's get into the actual numbers. We are taking the derivative of a at x is equal to negative 5 over 12 x squared plus 5x. Just using the power rule, we bring the 2 down from the x squared and multiply it by negative 5 over 12, which gives us negative 10 over 12, which simplifies to negative 5 over 6 times x. And the derivative of 5x is just 5. So our final derivative function is a prime at x is equal to negative 5 over 6x plus 5. And this new equation just tells us what the exact slope of the area at any point x. Now to find the maximum, we set a prime at x to 0. So we subtract 5 from both sides, then multiply it by negative 6 over 5, and we get x is equal to 6. This tells us that for this specific triangle, the rectangle achieves its maximum area when its width is exactly 6 centimeters. Now that we know x is equal to 6, we just need to find the corresponding y value in the final area. So we plug x is equal to 6 back into our original height equation. Y equals negative 5 over 12 x plus 5. That simplifies to negative 2.5 plus 5. So y is equal to 2.5 centimeters. And now, for the grand finale. Area equals width times height. 6 times 2.5 gives us exactly 15 square centimeters. This is the absolute largest rectangle you could fit into a 5, 12, 13 triangle under these rules. Any other width, like 5.9 or 6.1, would give you a smaller area. Earlier, we found our first derivative was a prime at x is equal to negative 5 over 6x plus 5. To prove that our critical point, x equals 6 is a maximum, we use the second derivative test. And this is just a shortcut to check the concavity of our function. We take the derivative of our derivative. So the derivative of negative 5 over 6x is just negative 5 over 6, and the derivative of 5 is 0. So our second derivative, or a double prime x, is negative 5 over 6. And because this value is negative, it tells us that our function is concave down, like a frown, at every single point on the graph. In calculus, if your first derivative is 0 and your second derivative is negative, you have mathematically guaranteed a local maximum. This brings us to our final conclusion. By plugging in our optimized width of x equals 6 back into our height equation, we found a height of y equals 2.5, and when we multiply these two together, we get our absolute maximum area, 15 centimeters squared. This is the peak performance of our rectangle within this 15, 12, 13 triangle. It's also worth noting that the relationship between x and y could have been found using similar triangles, since the small triangle formed above the rectangle keeps the same 5 to 12 ratio as the original triangle. That would lead to the same height-width relationship we used when we found it using the coordinate plane. And finally, if we think about the possible values of x on a number line from 0 to 12, 0, because when we substitute 0 into our first equation, the box has no width, and with 12, the box has no height. So the area starts at 0, increases, reaches a maximum at x equals 6, and then decreases again. And the derivative simply let us find that exact peak mathematically.
Thank you so much for listening. I hope that you learned something new, and we hope that you'll be able to understand derivatives more and how it applies to real life as well through problems similar to these. Thank you.